With a little bit of work, we can do lots of antiderivatives now. Let's see, we have this complicated function, but we know that the antiderivative of the sum is the sum of the antiderivatives, or in this case, I guess the antiderivative of the difference is the difference of the antiderivatives. So we have the antiderivative of 1/2 cosecant squared x minus, with respect to x, minus 1/2 the cosecant antiderivative of cosecant x cotangent x dx. The 1/2s pull through, so if they're bothering you, you can just bring out any constant. And now we just ask ourselves, what function has a differential that's cosine squared x dx? Let's see, the derivative of the cotangent is the negative cosecant squared, so I think I could do negative 1/2 cotangent x, right? Because if I do that, the negative 1/2 comes through. I take the derivative of the cotangent, get the negative cosecant squared. That negative canceled by this negative, so I have 1/2 cosecant squared x. Okay, and here the derivative of the cosecant is the negative cosecant cotangent. I've got this negative here, so I think if I just do 1/2 cosecant x and then add in my arbitrary constant, I've got the antiderivative. You can always check by taking the derivative, right? Like the derivative of 1/2 cosecant x would be 1/2 of negative cosecant x cotangent x, which is negative 1/2 cosecant x cotangent x. This one's probably easiest if we break it up into two fractions. We have 1/2 minus 1/2 cosine 6t. So I just broke that into 1 over 2 minus cosine 6t over 2 and wrote it this way. Now the antiderivative of the difference, oops, this is not dx, it should be dt since that's our, okay, the antiderivative of the difference is the difference of the antiderivatives. So I can just focus on solving these two simpler problems. The constant 1/2 pulls through, so if it's getting in your way, just pull it out. You can pull it out of each of these. Let's see, so if I pull that out, I have cosine 6t dt, and now find both of the antiderivatives. Well, what has a derivative? Think of that as like 1 dt. What has a derivative that's 1? T does. Okay, minus 1/2. What has a derivative that's cosine 6t? Must be something like sine 6t, but then if you took the derivative of that by the chain rule, you get the derivative of the outside, which is cosine 6t, times the derivative of 6t, which would be 6. So I'll just put a little 1/6 in there to catch the 6 that comes out and add in my arbitrary constant. I could just simplify that. 1/2 t minus 1/12 sine 6t. Now I'm done. You might ask, well, you had two integrals. Why didn't you have two arbitrary constants? Shouldn't I have had another constant here? Well, you could think of it that way, but then if d and c are both arbitrary, then if you can choose whatever d is and you can choose whatever c is, right, they're arbitrary constants, you could make any other arbitrary constant from that sum. So you might as well just use one arbitrary constant. Just call it c. One more here. The antiderivative of 2 plus the tangent squared of t. Uh-oh. I don't know anything whose derivative is the tangent squared. I do know something whose derivative is the secant squared, and I also know there's a Pythagorean identity, because cosine squared t plus sine squared t equals 1. If you divide both sides by cosine squared, you get 1 plus sine squared over cosine squared would be tangent squared t, and 1 over cosine squared would be secant squared t. So tangent squared is actually secant squared t minus 1, which would be handy here because I do know the antiderivative of 1, and I know the antiderivative of secant squared is the tangent. So let me take this problem and I'll just rewrite this tangent squared as secant squared t minus 1 dt. Of course, the 2 and the 1 are both just constants, so they can be combined, and 2 minus 1 is 1. So I really just need to find an antiderivative of that. But the antiderivative of the sum is the sum of the antiderivatives, so I can find the antiderivative of 1 dt and add in the antiderivative of secant squared t dt. antiderivative of 1 is t, and the antiderivative of secant squared is tangent t. And if I throw in an arbitrary constant, then I've found them all.